introduce Alexej and we can get started. So first of all, thanks so much everyone for joining in the PAC seminar today. The PAC program actually is a representation of 3 different organizations. P stands for Penn State, and AC stands for American Ceramic Society, which has provided a great support for our program. And then K stands for Kiel. So that the Kiel serves as the host university for all the US students, which Penn State and American Ceramic Society together select. And these students spend 3 to 6 months of time at Kiel, understanding and learning different aspects of smart materials, magnetoelectrics, sensors, biomagnetics, very diverse range of topics. And this program has been supported by National Science Foundation through OISC, and NSF has really conceived this very creative program to provide and engage students from all over the world with each other. So our students, the first cohort, had the chance to spend their time and learn many different things in thin film lab and in magnetoelectric device lab. And our second cohort, because of COVID, has been delayed. But we are hoping that the second cohort can start to arrive in Kiel in early January. So at this point, we are collecting actually applications for second cohort, and we are making down select. And hopefully we'll finalize the list of students in a month or 2 that they can start to arrange their travels. So if you're a student, a PhD or master's, and you are a US person, you're most welcome to apply. Just send your application directly to Sadie Spicer on the call, or you have received email from Sadie, and she will get the process started for your application. And so in this PAC program, one of the activities we do is organize these online webinars. And this is one of the ways we educate our students, both in US and in all over the world. And all the great speakers who have come in this PAC seminar, they have provided a very basic tutorial or some background information about a new topic. And over the course of last several months, we have learned many different new topics. And so today is a very exciting topic of superconductors, which is probably one of the most famous and popular topic in the world. And we are grateful that Alexej was able to find time and pull together this presentation for us. And he has a lot of experience in this area. Alexej is very, very diverse researcher, has done a lot of research in many different domains, like 2D materials and optical materials, and now is working on acoustics. So he's very well renowned in many different areas. And so I'm very thankful that Alexej was able to find the time to come and give this seminar to you. And I think you'll learn a lot of new things today in this talk. So thank you, Alexej, and I'll pass it on to you. Yes.
Thank you, Professor Priya, for your introduction. And good morning, everyone at Penn State, and guten Abend for the attendees of the seminar at Kiel University. The subject of this talk is superconductors, science and application. And at first glance, it would seem that this subject is out of framework of the PAC program, but actually it's not the case, because high temperature superconductors are in effect ceramic materials, and they possess all the properties of regular ceramics, and this affect superconducting properties, as we will see later today. Let's start, and let's start from the beginning. Almost over 100 years ago, at low temperature physics laboratory at Leiden University in Holland, director was Camerlin Onnes, and in 1908, they succeeded in liquefying the last noble gas, helium, and this vastly expand the areas of research in the low temperature physics, opening the possibility to do research closer to absolute zero. At that time, the mechanism of electrical conduction was poorly developed. So there were several ideas, as shown on the plot on the right. For example, James Dewar suggested that the lower the temperature, the lower the resistivity would be, and eventually the resistivity will tend to go to zero, as shown here by the curve numbered 1. It was also known that materials would have some residual resistivity. So at room temperature and slightly below, the resistivity was going linear with decreasing temperature. But then this dependence started to deviate from linear dependence. And so the idea was that probably materials would be reaching some residual resistivity. The third proposal came from Thomson, very famous physicist, Lord Kelvin. He suggested that the resistance would go through a minimum and then would start rising again, and the electrons would adhere to corresponding atoms. So Cameron on us studied investigations of electrical conduction of pure samples of gold, platinum, because the samples at that time could be obtained in pure form. But then he switched over to liquid metal, mercury, because after consecutive distillation, that material could be obtained in very pure form. And after some time, what was found, instead of all these predictions, that the resistance of the mercury sample dropped down within a fraction of a degree to a so low value that could not be measurable with the apparatus that were available for electrical resistance measurements. And as Cameron Honest wrote in the proceedings from that institute, that this sample passed to a new unknown state that he called superconductive state. So he himself coined this term superconductors, superconductivity, and so on. So this is one of the main characteristics of superconductors, that at some temperature, which is called critical temperature, the electrical resistance go to the level that is that cannot be measured. Actually, experiments can be done and were done that consisted in inducing a superconducting current in a loop of superconducting sample, and the measurements were done of the decay of the current with time, as shown by this equation. And for example, in 1962, after 2 years of these studies, it was found that the upper limit for resistivity of superconducting state was 10 to minus 24 ohm centimeter. For comparison, at the same temperature of 3 Kelvin, the resistivity of copper is 5 times 10 to minus 9, ohm per centimeter. So the difference between this conductivity of superconductor and copper is similar as the difference between the conductivity of metals and insulators. And recent data in Belgium, they were conducting gravimetric studies using superconducting gravimeters, and the persistent current as of today, July 2021, persisted for over 26 years. So this is one of the main properties of superconductors. The next very important property of superconductors is magnetic flux expulsion. It was discovered by Meissner and Oxenfeld in 1933, and currently it is referred to as Meissner effect. It turns out that if we place a superconducting material into a magnetic field, then at temperatures when that is higher than the critical temperature, then this material is in normal state. Then if we just decrease the temperature, the magnetic flux will be expelled from the interior of the sample. This is a Meissner effect. So superconductors behave as perfect diamagnetics. Magnetic susceptibility equals to -1. This brings about very interesting effect as magnetic levitation. If one places a sample of ferromagnet over the superconducting material that is in superconducting state, as shown here, it will float over the surface of superconductor. And let's watch some video. If we are lucky, it will work. So what you see here is a rotating ferromagnet sample of the high temperature superconductor that is placed in the liquid nitrogen, and its temperature is below superconducting transition temperature, so it's in the superconducting state. This is another example. So what happens actually is that magnetic flux is zero in the interior of the sample, but magnetic field penetrates into the surface of superconductor, and according to this expression, it's exponential dependence, and the length constant is called penetration depth, marked here as lambda. And so at this surface layers, there is a current, normal current, that creates magnetic field that exactly cancels the magnetic field from the external source. And that's how the magnetic field inside the sample becomes zero. So parameters of superconductors, first of all, we already saw that that was a critical temperature. Then there's critical magnetic fields. There are several critical magnetic fields. First of all, it's thermodynamic critical magnetic field. It's characteristic for type 1 superconductors. So superconductors can be either in Meissner state where there is no magnetic field, or if the external field exceeds the critical magnetic field, the superconductor goes over to the normal state. And of course, this thermodynamic critical temperature depends on temperature, and it becomes zero at critical temperature of a particular superconductor. So this plot shows the dependence of thermodynamic critical field for mercury that has a critical temperature of 4.15 Kelvin. So there is another type of superconductors, and most of the superconductors are type 2 superconductors. They have two magnetic critical fields, lower critical field and the higher critical magnetic field. And the phase diagram is as follows. For relatively low external magnetic fields, the sample is in Meissner state, so no penetration of magnetic field, magnetic flux into the interior of the sample. But if the external magnetic field exceeds the lower critical field of a sample at a particular temperature, the magnetic flux starts to penetrate into the sample, and it penetrates it as a vortex lattice, as shown here on this cartoon. And here is the top view of scanning tunneling magnetometry. This is the scale bar is 6,000 angstroms. So we see this is a perfect ordered lattice of magnetic flux vortices that penetrate into the sample. Within these vortices, the sample is in normal state, and outside the vortices, between the vortices, it's still in superconducting state. And only the external, after external magnetic field exceeding the upper critical field, the sample becomes fully normal, no superconductivity. And for example, this plot shows that lead, pure lead, is a type 1 superconductor, as shown here by dashed line. It has particular thermodynamic critical field that is below 600 Gauss, but the lead alloyed with indium is a type 2 superconductor. And here we see that this peak corresponds to lower critical field, and this value of about 2400 Gauss is upper critical field for lead indium alloy. This magnetic flux quanta contain a quantum of magnetic flux, which is shown in this expression. H is a Planck constant, and E is electric charge. Electric charge of the electron. And one more parameter of superconductors is critical current density. So superconductors can carry a current, but if the current strength or critical current density exceeds some critical current density exceeds some critical value, superconductor goes over to the normal state. If we pass a current along x direction, as shown on this cartoon, and turn on the external magnetic field normal to the current direction, then in pure and very ordered samples, the vortices start to move, and the movement is caused by Lorentz force. So, and this movement will bring about dissipation. So, although the sample will be in superconducting state, the current will dissipate, and there won't be persistent current in the superconducting samples, although it is in superconducting state. So this phenomenon is described by flux flow resistivity, as shown in this expression. So to prevent, suppress the dissipation, to make the current flow without resistivity, as in resistance, as it should be in superconductors, we have to prevent this vortices from moving. It is made by making the samples dirty. This is jargon in superconductor community parlance. So making samples dirty can be achieved by alloying, adding some particles, or irradiating, creating defects, structural defects. Polycrystalline samples, grain boundaries of the samples will act as pinion sides. So vortices will be attracted to these centers, and unless the current is so strong that the vortices will tear of this pinion sides, there will be no movement of vortices, and the current will flow without the resistance. So superconducting materials. Here we see the periodic table, and blue color marks the elemental superconductors that are superconductors at ambient pressure. And here we see just examples of some elemental materials with corresponding critical temperatures. So the maximum critical temperature of elemental material is 900.25 Kelvin for niobium. And there are samples with very small elements with very small critical, very low critical temperature. By green color, mark the elements that become superconducting at higher pressure. So these are elemental superconductors, but there are a lot of superconducting alloys. For example, there are many metallic alloys, and many of them are used in applications. So we continue on superconducting materials, and here we see that in 1986 there was discovery of high temperature superconductivity in this complex oxide, lanthanum, barium, copper oxide. And just after several months after this discovery, the critical temperature was raised from 30 to 92 Kelvin in yttrium, barium, copper oxide. After that, during this time after this discovery, they were discovered multiple high temperature superconductors of this family and other families of superconductors. For example, high critical temperature superconductors that contain iron. That was considered a no-go in the superconductivity research. It was considered the iron was because it has ferromagnetic properties. It was and the magnetic field suppresses superconductivity. It was thought that no way that samples containing iron would have appreciable value of critical temperature. It turned out that that was not right, and these materials have critical temperatures of about 55 degrees Kelvin. So what we see is that here this colored cartoon shows the atomic distribution in E3 barium copper oxide, and copper atoms are shown here, and oxygen atoms are shown here, and red spheres stand for barium, and this yellow-green spheres stand for yttrium atoms. The conductivity or superconductivity occurs within this copper oxide planes. So these samples have highly anisotropic properties. Conductivity within these planes are much higher than conductivity in the normal direction. So this is typical ceramic superconductors. They're brittle, and we'll see how it affect the properties of, in particular, current carrying capabilities of these materials when we go when we discuss the applications. So conventional superconductivity, after the discovery of superconductivity and up until 1957, the mechanism of superconductivity was not understood, despite many brilliant minds that tried to tackle this problem. In particular, so many, I won't dwell on it. Many researchers, very famous theorists, try to solve this problem. It was not they could not succeed. So the first indication come from considering interaction of electrons with phonons in solid state. So Froelich in 1950 theoretically showed described this electron-phonon interaction. In particular, electron-phonon interaction brings about the resistance of the samples. The stronger electron-phonon interaction, the higher the resistance of the sample. The next year, it was found that mercury has isotope effect. So when adding atoms with the same atomic number, so with the same chemical element, mercury, but the atoms of different atomic weights would change the critical temperature of the mercury, which meant that somehow the lattice, ion lattice, is involved in the superconductivity. phenomenon. And in 1956, Cooper showed that, again, theoretically, that the electrons with opposite momentum and opposite spins would have a strong correlation, and this correlation would depend upon the interaction between these electrons. Any attractive interaction between electrons, however small, would bring about brought about the correlation between these pairs of electrons. And in next year, Bardeen, Cooper, and Schrieffer produced eventually the first successful theory, microscopic theory of superconductivity based on this property of Cooper instability and Cooper pairs. So in this theory, which is referred to as Bcs theory, electrons in a superconductor at low temperatures are coupled in pairs. And coupling is due to interaction between electrons and crystal lattice. So since normally electrons, being fermions, cannot occupy the same quantum mechanical states, and they will be repelled from each other strongly by the Coulomb forces. But when they form Cooper pairs, then this composite creatures, Cooper pairs, will have zero spin, and then they will act as bosons. And bosons are quite different from fermions because they can occupy the same quantum mechanical state, as we can is well known in lasers, for example, that photons can go into the same emitted photons go into the same state. That is why laser radiation is coherent, and this they have all the photons. The more the number of photons, the more readily they condense in one particular quantum state. So that is why the laser radiation is monochromatic, is one color, and so this is a property of bosons. So again, the bosons, unlike fermions, do not obey quantum mechanical exclusion principle. As a consequence, the Cooper pairs act in a correlated way. So this is a collective state, and they, similar to photons, they could move all together. So this is a cooperative phenomenon. A very very crude way to imagine why electrons in a lattice form Cooper pairs would be just consider one electron that moves along this ordered rows of ions, and this electron would attract these ions, and so it it polarizes the lattice. Next electron that would move after this would feel that there's a increased positive charge. And so that's how this electron, second electron, would be attracted to the first electron via this lattice polarization. That's how this picture of superconductivity works. And but this is a very crude approximation, and actually in quantum field theory, this process is considered as one of the electrons with momentum k emits a phonon with momentum q and is scattered with k minus q momentum. The next electron absorbs this phonon, and this scattering. So this scattering process will brings about this correlation between these two electrons. The critical temperature was obtained in this Bcs theory. We can see that this is some characteristic frequency of a material, in particular Debye frequency. And here we see that in the exponent, there's electronic density of states at Fermi level, and V stands for attractive electron-electron interaction, and the attraction comes from Froelich electron-phonon interaction. So superconductor is described by microscopic many-body quantum wave function, and to break the Cooper pair into particles, one has to apply an energy to delta, and the Cooper pair size or coherence length c shown here is Fermi velocity, Planck constant over this delta, which is called superconductor energy gap. And in regular Bcs superconductors, this coherence length is very large compared to the distances between the conducting electrons. So there is a lot of Cooper pairs that are interpenetrating into each other. So this is a correlation. That is why this superconducting state is so stable. It's it's difficult to break a single particular Cooper pair because they're all interconnected in correlations. Currently, so this theory, Bcs theory, was developed further in several years after the publication, and the theory of superconductivity was the most accurate physical theory in condensed matter physics. High temperature superconductors that were discovered already over 30 years ago have much stronger interaction between the electrons, and this superconducting energy gap is much larger. So the Cooper pair size is much smaller, as shown on this cartoon. And up to now, there's no theory, accepted theory of superconductivity in high temperature superconductors. So let's see how this superconducting energy gap, where it opens. So here we see energy band diagrams of various materials, insulators, conductors, and semiconductors. And in insulators, we see that the valence band is fully occupied and the conduction band is fully unoccupied. So there is no conducting electrons. So the insulators are insulating. In conductors, there is some number of occupied states in the conduction band, but other states are unoccupied. So when we apply the voltage, the electrons can go over to other empty states, and that's how the current can be transmitted by conducting materials in metals. And semiconductors are similar to insulators, but the band gap is much smaller than in insulators. So if you look at the metals, so normal conductor, so electrons occupy energy levels in the conduction band up to maximum, some maximum energy, which is called Fermi energy. And when in superconductors, the gap arises between the occupied states and unoccupied states, and this gap near the Fermi surface, or around the Fermi surface, this gap is equals to 2 delta, 2 superconducting gaps. This value of superconducting gap actually can be measured, directly measured. In 1961, Geyer conducted experiments. He was passing current between the normal metal and the superconductor, and these thin films were separated by dielectric barrier, alumina in particular. So he studied, he deposited aluminum films on glass substrates, oxidized aluminum, and deposited on top of this material other films. So what was found that the current was not passing up until some value of applied voltage, and this value equals exactly of superconducting energy gap in a superconductor that forms this junction. And
3 minutes.
as again,
3 minutes. So we have time for questions, please.
wasn't it 45 minutes?
Yeah, if you that's all you have left, we can finish it. I just wanted to make sure there was some time at the end for questions. You can continue.
If we decrease the barrier thickness to 10 angstroms, we would have Cooper pairs tunneling. That was predicted theoretically by Josephson in 1962. And this, there are 2 types of Josephson effects that occur in this type of junctions. Constant current Josephson effect and alternating current Josephson effect. These effects are widely used in applications. For example, this second Josephson effect is used in frequency to voltage converters and used in voltage standards. And here we go over to the applications. Here we see that Josephson junction arrays are used in standard of volt For example, this is the same layout. This is a SEM image of layout of 208 junctions for 10-volt Josephson array voltage standard tip. That's because every particular, why such a large number of junctions? Because the voltage drop on each particular junction is very small. So to get 10 volts drop, we have to have arrays of the junctions. So superconducting electronics is based on Josephson junctions. Here we see examples of microcircuits, superconducting microcircuits, and they are made of various numbers of Josephson junctions. This is a cross-section of superconducting circuits, so it's a multi-layer structure that contains junctions at different layers. So these Josephson junctions are used in high-speed electronics, and in particular in superconducting supercomputers, as shown here for the D-Wave company. This is a working quantum computer that contains 128,000 junctions. So these are applications of superconductors in electronics. Single Josephson junctions. Now, if you put these Josephson junctions in a superconducting loop and apply pass the current through this loop, the current will split between these shoulders and go into, and then combine into the this left electrode. In the absence of external magnetic field, the system will be these currents will be equal. But if we apply external magnetic field that will penetrate through this ring, it will induce a circular current that will be added to this current that is passing through, and it will change the current through each of Josephson junctions. In this way, we can modulate the current through the or the voltage. If we apply constant biasing current, then application of turning off external magnetic field will change the voltage drop on this structure. This is the basis of magnetometry measurements of extremely high sensitive magnetometers, which is used, for example, in magnetoencephalography. Magnetic signals of brain can be measured using magnetometers, these squid arrays, because the threshold of sensitivity for squids is near the quantum limit, about 2 times above the quantum limit. So the brain signals are much stronger than the sensitivity. So these magnetometers are currently used, and what we can see here is just cartoon that's showing that these arrays of magnetometers are conducted to electronics, and we can see the brain activity in vivo. So magnetic signals from the brain are much smaller than electric signals. So electroencephalography is measures much stronger signals than magnetic encephalography. but magnetic encephalography has many advantages. It has much higher spatial resolution, so one can carry out these studies and before the surgery to find the areas where the surgery should be done, areas of pathology in the brain where the surgery should be conducted. But in general, these two methods complement each other. And other applications of superconductivity include high power applications, where this levitation of magnets is used. So well-known bullet trains or maglev trains, magnetic levitation, uses superconducting cables and magnetic constant magnets that allow the train to be floated over the conduction path. Also, this superconducting magnets produce propulsion of the train. Also, the superconducting cables are used in motors for transmission very high density electric currents, and they're used in CERN, in particle accelerators, in particle for focusing the particles, for bending the particle beam, and for example, Siemens makes high temperature superconducting generators. Superconducting cables made of high temperature superconductors can be made out of round wires or after rolling from tapes. And here we see the cartoon showing the so-called second generation tape of superconductors. And superconducting wires can carry more than 100 times higher current density than equivalent copper wires. But because these are ceramic materials, they require some texturing. One cannot deposit high temperature superconductors directly on flexible metallic substrate. One has to deposit first buffers, or maybe multiple buffers, on top of which we can epitaxially grow a layer of high temperature superconductors. That is the cross section of a superconducting cable. And this is the latest achievement in the production of high temperature superconducting wires and tapes at a company of Teva. Last year, they have achieved the record of 1500 amperes per square millimeter critical current density, because of this, they found how to improve the process of fabrication. So thank you for your attention.
All right. Thanks so much, Alexej, for this great talk. I know we have only a couple of minutes for questions. It will be great if you have some for Alexej. Actually, I'm very impressed. Every time I hear about superconductors, you learn something new. It's such a complex physics and such exotic phenomenon. But one of the things which I would love to explore more, Alexej, is these magnetic measurements. So the best, we all know we use VSM machines, and some people use squid magnetometers for measuring the magnetic material properties. and its quits can go down to, I guess, go down to almost like a picotesla level
Yes.
measurement in an isolated room. So for us as a magnetic material researchers, we are always trying to find way to just push that measurement limits. Right? And same thing in biology, like the brain signals, especially the neuron firing, is on the order of like 0.1 or 0.01 picotesla level.
Yes, yes.
And if we can, for example, make a superconducting helmet, and it can start to measure the brain signals like a non-contact, non-invasive, that'll be great, but it just requires huge amount of magnetic bias, like several Teslas. And that's a challenge.
Yes, this is a fascinating properties of superconducting quantum interference devices with, yes, that's how the superconductivity is used.
Yeah, so both these measurement of magnetic materials and measurement of brain signals, would be, I think superconductors are the state of the art in both cases.
Yes.
But the only challenge is that it requires low temperature and it requires a huge amount of bias fields. And so any way to reduce both these things, and I guess this is the holy grail here, high temperature. And
that is why high temperature superconductors are widely investigated, and so many efforts were put into this trials to create this superconducting wires made of high temperature superconductors. Because, for example, in CERN, this latest experiments, they put in very traditional metallic niobium titanium wires that were developed. The process, the technology of production of these wires were developed in 1950s, and they still use this. Although just last year, General Electric produced magnets for the CERN that were made from niobium 3 tin that has about twice the temperature of niobium titanium alloy, and that allowed to make these magnets smaller and give this large physical chambers, which is the detector chambers, more space for upgrading these experiments.
Yeah, that's excellent. It's just an amazing topic, and continues to remain an very widely investigated topic. Yeah.
I have a quick question.
Yes, Sanjay.
So on the note of a high TC superconductivity, which is actively pursued, as you're pointing out, around 2 years ago or 1.5 years ago in 2019, I came across some work on where they achieved the superconductivity at room temperature. I mean, like 250K and 320K, something like that, on lanthanum hydrides, however, at very high pressure. So I think they are lanthanum based and yttrium hydride based systems. So can you comment on that? What's going on over there?
Yes, you're right. This a long time ago, Professor Mermin suggested that hydrogen, if it were condensed and made metallic, could be a high temperature superconductor. However, this condensing the hydrogen, making the hydrogen metallic would require some enormous pressures. So these recent experiments that you mentioned, they succeeded in so from 60s of last century to up to now, they improve this technology of producing high pressures, and they found that several compounds that contain lanthanides, lanthanum or similar atom, and like 10 atoms of hydrogen, so it's almost pure hydrogen, but contains some lanthanum atoms, can be, what they see is jumps in resistance at very high applied pressures. These experiments, the volume of the samples is in tens of microns, and they are non-uniform. So it's, although they already measure the structure and other properties, there were some objections that these were superconductors. Superconductivity brought about these drops in the resistance, because just changing the crystal structure may drop the electrical resistance. So the teams that carry out these experiments strongly believe that they measure superconducting transitions, but there are some objections to that. And again, the level of pressures that I applied, you know, the Mariana Trench in the Pacific Ocean near Japan. So the pressure at the bottom of this Mariana Trench is about 1,500, more than 1,000 times smaller than the pressure that they apply at the laboratories. So this, again, this is, of course, a very important development. And let's hope that at some point these materials will be available at regular pressures, and then we would have room temperature superconductivity.
Right. Yeah, it is a very interesting topic, actually.
Yeah. Okay, so thanks so much again, Alexej, for taking out the time to talk to us. I really appreciate it. And thanks so much, everyone, for joining in. Many of you already know Alexej, so please communicate if you have more questions.
Thank you for your attention. Thank you.
Yeah, thanks very much, everyone. Enjoy the rest of the day and have a good weekend. Yeah.
Have
Bye.
a good weekend.
Yeah. Bye, everyone.
Bye-bye.
You.
Bye.